You know, have you ever really stopped to think about something as simple as the glow from a hot object? We're about to pull back the curtain on this everyday magic and show you the incredible, invisible dance that makes it all happen.
I mean, really think about it for a second. It's just a black coil, right? You flip a switch, and a few moments later, it's radiating this intense, deep red. Why that color? Why does it glow at all? What is actually going on there? Well, the secret isn't something you can see on the surface. Nope. It's happening at a scale so small it's almost impossible to imagine. A chaotic, ridiculously high-speed dance of microscopic particles. And that's exactly what we're going to do. We're going to dive in and figure out the fundamental rules of this invisible dance. Why? So we can finally understand exactly how heat creates light. So, to get our heads around this, we've got to start with the simplest version of this dance, the one we find in gases. Just picture it. The air all around you right now is just trillions upon trillions of tiny molecules behaving like microscopic, super bouncy balls. They're in constant, random motion, smashing into each other and bouncing off in this state of beautiful, perfect chaos. Now, to even begin to make sense of all that chaos, scientists have a trick. They start with a simplified model they call an ideal gas. Think of it as a perfect world where these little particles never stick together or push each other away. It gives us a perfect baseline for understanding the much messier reality of a real gas. And here it is. This is kind of like the master rule book for that whole dance. The ideal gas law. It's this incredibly powerful little equation that connects all the stuff we can easily measure, like pressure and volume, to the one thing that holds the key to the glow: temperature. And believe me, that T is way more important than you think. All right, so let's dig into that T for temperature, because it's probably not what you think it is. See, it's not some abstract thing. It's a direct measure of the energy in that invisible dance. So if temperature is all about movement, just how fast are we talking here? What's the speed limit for, say, the particles in the air right here in this room? Get this, an absolutely staggering 517 meters per second. That's over 1,150 miles an hour. So the seemingly still, quiet air around you is actually a hurricane of particles moving faster than a jet plane. And that, right there, is the big secret. Temperature is just our way of measuring that speed. It's the average kinetic energy, the energy of pure motion of all those dancing particles. So when you heat something up, all you're really doing is making its atoms and molecules dance faster and faster. Okay, so hot things have faster moving molecules. Got it. And this isn't just for gases, right? The atoms in that solid stove burner are just vibrating like crazy. But how does all that jiggling turn into a visible glow? Well, that brings us to radiation. Here's a fundamental truth of the universe. Anything and everything that has any heat at all, and that's everything above the impossible cold of absolute zero, is constantly shedding energy. It's broadcasting it out into space as electromagnetic waves. We call this thermal radiation. Now, when that energy hits another object, it's got to do one of three things. It can get absorbed and turned into heat, it can get reflected, like off a mirror, or it can pass right through. That's it. Every single bit of that energy has to go somewhere. To study this perfectly, physicists came up with another one of those ideal concepts, the perfect blackbody. It's this theoretical object that's the ultimate energy sponge. It absorbs every single bit of radiation that hits it. Nothing gets reflected, nothing passes through. So here's the cool part. If this thing is the perfect sponge for soaking up energy, what happens on the flip side? What happens when it gets hot and it's the one giving off the energy? Turns out the answer is beautifully simple, and it comes from Kirchhoff's law. It's a two-way street. An object's ability to give off energy is exactly the same as its ability to take it in. So a good absorber is also a great emitter. Our perfect blackbody isn't just the best at soaking up energy, it's also the absolute best at radiating it away. And this is where it all comes together. Because when an object radiates all that energy away, it doesn't just release invisible heat, it releases light. It's the glow we've been chasing this whole time. At everyday temperatures, that radiation is totally invisible to us. It's in the infrared part of the spectrum. But then you start cranking up the heat. Once you hit around 800 degrees Celsius, boom, it starts to glow red. That's our stove burner. Push it even further, up to 3,000 degrees, and it becomes a brilliant white hot, like the filament in an old light bulb. And there's a simple rule that explains this color shift. Wien's displacement law.
The easiest way to think about it is this. The hotter an object gets, the more energy it has to throw off. So it starts emitting light with shorter, higher energy wavelengths. It moves from those long, lazy waves of red light up towards the shorter, more frantic waves of blue and white light.
And this simple idea is incredibly powerful. I mean, we use this exact principle to measure the temperature of stars millions of light years away. We can look at a star's color and know if it's a cooler red giant or a blazing hot white dwarf. It's the same science a steelworker uses to judge the temperature of metal just by its color. It is cosmic and it is industrial.
But the color is only half the story. The sheer amounts of energy being blasted out is also skyrocketing. And this is where things get, well, kind of crazy. The Stefan Boltzmann law tells us that the total energy radiated is proportional to the temperature raised to the fourth power.
I mean, really let that sink in. If you double an object's temperature, you might think you'd get, what, twice as much energy? Nope, you get 16 times more. This explosive relationship is why hot things get so bright so fast. It's why the sun is so unbelievably powerful. That's the power of T to the fourth.
So we're left with one final mind-bending question. If you, me, this desk, everything in this room, if we're all constantly radiating energy because we have heat, why isn't the world just constantly glowing? Well, the truth is, it is. We are glowing. It's just a light our eyes can't see. We are all part of that same invisible dance, radiating our own unique heat signature out into the universe. And with things like thermal cameras, we can finally get a peek into this hidden, glowing world that's all around us.